All right, so we went through that chapter on pressure. I think we got through it pretty well. We just kind of hit the highlights on this. So this starts on about page 62. It's 59, and it goes through 77. All right. So the basic definition of pressure is a force divided by an area. Okay, that's the basic definition. Okay. We came to the really important conclusion that 1 foot of water is 0.433 psi. Okay. So that's really important that you know that. We'll use that plenty of times. And the important thing about this is that it does not depend on the size of the body of water. It holds for any size body of water. So generally, a mistake that people will make if they make a mistake with this is they make it too complicated. Okay, 1 foot of water gets you 0.433 psi. That's all there is to it. Okay, nothing more. Okay. And we went through a few examples of that. There's one page that's devoted exclusively to that idea and kind of has a whole bunch of different containers. And this is page 64. And the idea is that every situation there, if it's 12 feet deep, the pressure is 5.2 psi. That's it. Okay. So page 64. All right. All right. Went over piezometers a little bit, which are just a column of some sort of fluid that's used to measure pressure. Then we talked about atmospheric pressure, that's basically the weight of the atmosphere over your head, over a square inch of your head, you might think of. That's what you get in PSI. Okay. And we came up with quite a few different ways of measuring that and measuring vacuums. Okay. And to that point, there is a chart on your formula sheet that looks like that. That's one way to work through those problems, is identify your unit system, figure out what percentage is on either side of the value you're looking at, and then use that to find the other units that are used to measure that pressure in the vacuum. Okay. So we good with that? Okay. And then we did a couple special applications with manometers. Find the pressure required to hold up the mercury on one side, but then subtract off the pressure required to hold up the water on the other side on this one. And then we did this little deal here with a bubbler gauge, where you're actually finding the back pressure that you're pushing the air bubbles out against. Okay, so if it's 26 psi that you're reading on your gauge, that correlates to 60 feet of water, 60.1 feet of water. If you can then, that's the water above the bottom of the bubbler tube there. So then you can figure out how deep the well is from there, knowing that. Okay. So, we got any questions on any of this stuff? We went over some of this last time. No? We good? Okay. All right, so the key ideas we're dealing with here then are the idea of density and specific gravity that we covered in the first chapter. This one we covered that real fundamental relationship that 1 foot is 0.433 psi. You could also invert that and go 1 psi gets you 2.31 feet of water. You can go either way with it. Okay, and then we looked at that atmospheric vacuum stuff, and then just did some applications of this stuff. Okay. All right. Why don't we look at the next one down the line here if we're good with all that, and let's look at force. Okay. Okay, like we went over forces of push or a pull. I'm on page 78. Okay, so a weight is a type of force, probably the most common type that we deal with. And there's a water tank. That's the one of the Albany water tanks. What's going on there? That that weighs a lot. I mean, obviously, it pushes down on the footing underneath it. That pushes down on the soil, and all that stuff has to be engineered to be sure that the soil can handle all that force pushing down on it. Okay, so there are different ways to calculate force. If you're looking at fluid force, the quick way to do it is just find the weight of the water. That equals the force. Okay. So I've got an example there. If you've got a tank that has a 30-foot diameter and a 40-foot height, let's figure out what the force would be. It's simply equal to the weight of the water. So why don't you work through the volume of that tank and then multiply that by the unit weight of water, 62.4 pounds per cubic foot. Let's see what kind of force is pushing down on account of that. So you've got a diameter on the thing. We're going to take half the diameter to get the radius when you want to find the area. So it's pi r squared is what you're looking at there for the area. And then multiply that by the depth and get the volume. And then multiply that by the unit weight of water, which is usually taken to be 62.4 pounds per cubic foot. Let's start with the area, pi r squared. Get that. When you finish this up, you ought to get about 1,760,000, something like that for the weight, something like that. Okay. You'll get an area, okay? 707, thereabouts. You want to get the depth into that. That gets you the volume. And then multiply that by the weight of water per cubic foot. That's on your formula sheet. And that's one of those numbers, if you do this stuff enough, you probably couldn't even forget if you wanted to. Okay. Get the volume. 28,274 thereabouts.
28,260.
Yeah. first engineering project, going out with a nice clean set of blueprints, straight lines, pipes, all that. Look at that site and I said, man, this is a big pile of dirt. This is not what I'm seeing on these plans. There's bulldozers running around.
You don't get a sterile work environment.
Yeah.
Do you want paper?
No, I don't think so. Not even close. Not even close. Mm-hmm. So we get to that volume? Okay. And then you got the, what waterways, right? So this is probably the easiest way to solve this, okay? Just multiply it out, and you get a very big number. Water is heavy stuff. If you ever, backpack in dry country or something like that, you'll figure out how heavy water is pretty quick. It weighs a lot. A gallon of water is more than 8 pounds. Okay. You good on that? So 1,700,000 and some odd, and as I just mentioned, you might got a little different answer. We're fine. You're not going to design that footing any differently if you've got 1,759,000. You do the same footing. Okay. All right. So we good on that? Now there's another way to do it. This is how I would do this problem. I just figured out the way to do water. But I want to point out there's another way to work into it. And we're going to use this other method for some other things too. So let's kind of have a look at that, all right? If we're good. And this is on page 79, okay? All right, so what we got is we've got that the definition of pressure is force over area. That's an algebraic equation. You can multiply both sides by A and get the force is the pressure times the area, okay? You can do it that way too, okay? So this is just another way to work through what a force would be. Take the pressure times the area. This stuff all just kind of comes out in the wash, if you know what I mean, okay? All right. So let's find the average pressure on the floor, okay? We want to find the pressure and force being exerted on the floor. Well, what's the pressure on the floor? Given what we just went over yesterday, or day before yesterday, Monday. 40 feet times what? Yeah, right. That's just every time, PSI per foot. Okay, and that comes out to be 17.32. Now, the way I have that written, I'd write that out PSI. If I want to be a little bit more careful about that, I'd realize that PSI is pounds per square inch. Okay? Now, pounds is abbreviated LB, and I think that has to do with the Latin word for pounds, I think. It's kind of a weird abbreviation for pounds, frankly. I think it has to do with some sort of Latin word, I think. I'm not sure, but I think so. Okay? So what that tells us is every square inch of that footing has 17.32 pounds pushing on it. So now if we can figure out what the area is of the footing, we can find the total force, can't we? We can multiply that pressure times the area. That's the idea on this. All right. Now, the one little thing on this, though, is just be sure that you're using the right unit, see? Because that's pounds per square inch. It's not pounds per square foot. It's pounds per square inch. So the radius here of this floor is 30 feet divided by 2, which is 15 feet, right? So we use the radius, at least I do when I find areas. But I want to be sure I've got that in inches. Okay, I got to watch my units. So 15 feet, 12 inches per foot. That will get me the radius in inches, which is what I want, because that will allow me to find the area in square inches. Okay? So 15 feet, 12 inches per foot, 180 inches. That's the radius of the floor in inches. So are we doing all right with that? So find the area of the floor in square inches. That's the next thing to do. So see if you get the area of the floor in square inches, and as you might imagine, it's an awful lot of square inches. If you laid out an inch by inch grid on that floor, there'd be a lot of boxes there, right? And you ought to be getting more than 100,000 square inches when you do that. Okay? And then you can multiply that by the pressure, and that's another way to get the force. Okay? So get the area of the tank floor. Pi r squared, but again, r's got to be in inches here. You got to be thinking ahead on units here with this stuff. The units got to match, you know. And that's one main way I kind of keep track of what I'm doing. I just watch my units. Okay. Ah, that's not right. That's the wrong number. $101,788, something like that. Now again, you know, you might get something a little different. If some of you I've noticed don't have scientific calculators, you might be using 3.14 for pi. You're going to get a little different answer. Okay. No big deal. All right. And then you just multiply that by the pressure. That'll get you the net force. So we're going to get to the same thing. We're just doing it in a different approach. And you know, that's not all bad if the answers agree, right? I mean, I got a friend who he's an architect. He just works for himself. When he bids jobs, he does it 3 different ways. And what he's looking for are all 3 ways to come up with the same bid. Okay. That way he's confident that he's bidding it properly and he's not going to underbid something, lose a bunch of money. Okay. So 2 different methods to do the same thing. Okay, and kind of unit-wise, we know that every square inch has 17.32 pounds. And we know that we've got 101,788 square inches. And this time I get 176,961 pounds. On the previous page, I think I got 1764318 pounds, okay? The reason is there's some conversion factors here that are rounded. Okay, I use 2 different methods, and they're related to each other, of course. But when you start saying 1 foot of water is 0.433 psi per foot, it's probably 0.4333333. We've rounded that number. And when we say water 62.4 pounds per gallon, well, or cubic foot, that's rounded, okay? So everything's rounded a little bit. So here's a real good example. You know, I keep talking about this. I'll probably stop here after a while because I think you're getting it. But those are the same answer. You're not going to design a different footing for those 2 things. Okay? They're the same thing. And the other thing is look at the significant figures. The lead figure is the same, right? 1 million. The 760,000 is the same. The differences show up in the 4th figure. That's less than a % difference. That's you know, it's minor. Okay. All right with that? Okay. Now that's a downward force. Okay, that's pushing down. Now when I think of pushing on water, I think of just having a bunch of marbles and I push on it and they're going to go all different directions. See, pressure goes in all different directions. It goes down, but it also goes to the side. It even pushes back up too. Okay, so this type of thing goes sideways too. All right. Now, if you ever, I do civil engineering, so I notice stuff when I walk around. Y'all seen those little fire valves there? I think they're just meant to hook a fire hose up to if there's a fire up here. They don't have a hydrant up here, obviously. So that'd be a little funny, but okay. So let's have a look at that. I looked at that thing. You might even be able to read it. It's a 2.5-inch valve right there. Common pressure, 20 or 30 psi. Let's say it's 30 psi. Let's say we got 30 psi on that water, and I don't know if we do. We're kind of at the end of the line here, at the end of the Albany system, actually. So the pressure may not be quite that high, but let's just say it is. So, 30 psi on that valve. Well, how much force is going to push here? How much? When you put that cap on there, what's going on? Okay, how much force is going to push the cap off? Because we got to think about that. Right? When you design a cap, it's got to handle that. All right, and that should say inch there, 2.5 inch. So what's the area of the opening for that valve? Okay.
4.9 inches.
Is it? Okay. Because we go pi, and when you spec out things that are round, right, you use diameters. That's how you spec out pipes and valves and barrels and all that. I mean, round things are normally called out by diameter. So 2.5-inch gate valve, that means the radius is half of that. So it's 2.5 over 2. It's 1 1/4. So the radius then is 1.25 inches, right? So if you want that area, then you're going to factor that up. Okay, so the area will be pi times that 1.25 inches, and you square that. And is that the 4 point whatever?
4.9, yeah.
4.9? Okay, thanks. So that's 4 point.
Check my logic.
Yeah, I think we're good. Okay, and that's square inches, right? All right. Now figure out what the force is. If you know that area is 4.9, what's the force then? Yeah, right. It's pressure times area, nothing fancy. Yeah, it's right. It's 30 psi, and it's going to be pounds. Is what we're going to get out. Just a straight push. Okay. All right. So the force is the pressure times the area. So the force will be the 4.90. Whoops. I'm sorry. I'm doing it out of order. 30 psi for the pressure. Times 4.90 square inches. And what would that come out to be? Okay. All right. So whoever designs that cap, they better be sure the threads on that can hold 147 pounds, because if they can't, you got a problem. Okay. All right. All right with that? Okay. All right. What's minimum required water pressure in town? Anybody know? Okay, if you call up City Albany and say the water pressure in my house is low, what are they going to do? They're going to come to your meter, which is kind of the boundary between their system and your system. You with me there? Yeah. Because they build a service out from their main to the property line. They put a meter in there. Up on the city side of that, that's the city's problem. On the other side of that, that's a plumbing problem, and that's your problem, okay? So the meter is like the boundary, right? So if you call them up and say, I got low water pressure, they're going to come. They're going to shut that angle valve on the meter. They're going to pull the meter. They're going to put a pressure gauge on that valve and open it back up. And they're going to read pressure, okay? And if it's 20 psi or higher, they're going to tell you to hire a plumber. And if it's less than 20 psi, they're going to fix it, okay? That's how that works. So 20 psi is a minimum standard for city water, typically. Okay. Now that is one thing. To be aware of. When you're working for a city, you got to interface with the public, right? You got to learn some of those skills, just to tell people politely kind of what the deal is, in a reasonable way. They have to kind of understand that. Okay. The other thing is, when I say fix a water service, how does the City of Albany fix a water service?
Dig it up.
Dig it up?
dig it up, do you replace the pipe?
Yeah,
If it's a hot tap, there might be another valve in there, right on that 6-inch line,
Yeah.
that size, and do that.
right. So now, I think one thing to realize is this: if you're doing this, a major part of the cost is digging it up. That, digging's what costs money. Okay, so City of Albany, I think, approaches it the proper way. They dig it up, they replace it. They don't mess around with fixing water services. They replace water services is what they do, because they figure if there's one problem here in 3 months, I'm gonna have to dig it up again and fix another problem. So they just replace is what they do. Okay, and that just means putting in a new saddle, maybe. Okay, a new corp stop, service line, one is service line, new angle stop. New meter, or maybe not, yeah, new angle stop, and then tie that into the meter. Okay, so that's kind of the deal with that. Okay.
You get down, find the saddles loose.
What's that now?
Or you find the saddles loose and
Yeah,
tighten that up.
yeah, I know. There's
That's something.
there's lots of stuff, and it's stuff where you're in a trench, and that's not always quite as much fun. Being in the trench, it's easy talking about this stuff. A little harder being in the trench fixing it sometimes.
It's even worse when the water lines
Leaking.
lower than the actual level of the water table.
Yeah, I know.
There's holes in the water table right there, and some was about 4 foot.
Yeah, I know. A lot of places here in the valley, their water's up high.
Yeah.
It's a mess. There's also, you'll learn if you work for a city, there's a lot of places where you might have acidic soils, and they'll eat your services up pretty quick. There'll be some parts of the city where we replace them pretty quickly, others less so. All right, I don't know, you ever driven up Pacific Boulevard and look over there at the right when you cross Oak Creek? A little bit of a pump station there. You ever seen this little thing here? I couldn't get much of a picture through the fence, but that's what I got. All right, now let's see how about this one. Let's just say we got 40 PSI, which wouldn't be unusual for a force main like that. That's a pump station of some type. And that's about a 30-inch blind flange. A blind flange is when you just bolt a plate on a pipe, dead end it. Okay? Now, how much force we got on that thing? Let's figure that one out. Same process, different numbers. Okay? And I want to use 40 PSI for this just for fun. Okay. And this isn't in the book. I just making this up. Well, I didn't make it up. I went there and looked at it and took a picture. You should get a considerably bigger number on this one.
A little over 28,000.
Yeah.
2260.
Now, that's a different animal. I mean, 147 pounds out here, okay, whatever, but 28,000 pounds, that gets my attention, okay? And so be aware of this. If you got big mains, if you got dead ends on them, you got a heck of a lot of force. I heard a story once from a guy that worked down in Eugene. They had a main going down a hill, so they were building up extra pressure because they're on a big hill, and they hadn't buried it completely. They kind of left it in the trench and just put the bedding around it, and they pressurized it. And that thing just jumped up like a snake, and you got this big 8-inch water main just popping up out of the ground. It's like, just be aware, okay? There's just a lot of force that builds up. Okay? So, I don't know. So the area here, pi times 15 inches. But, this isn't it's significant. I mean, it's a big deal. So 707 again? Is that inches squared, is that right? And then the force is the pressure times the area. So the force is the 40 pounds per square inch. Remember, that's what PSI is. Pounds top, square inches on the bottom. 707. And that's the 28, whatever. Okay, so 28,274 or thereabouts. Okay. Whoop. So that's 14 tons worth of force on that, just on that. And look at it. Look at all the bolts on that thing, man. They flanged that up. I mean, that's a flange fitting for sure. And look at all the bolts. I mean, they're very conscientious about that. Okay. All right. I mean, that's some pretty. That's a big old valve. Look at that hand wheel in that thing. That's some big stuff there. Okay.
I'm just thinking of how much fun that would be having to talk those in the correct sequence.
Yeah, I know, and getting them right, and some jobs have a little higher liability around them than others, and they're more dangerous than others. Yeah, I know. But yeah, it had to be done right, I'm sure, because yeah, right. It's like a head, yeah, head of your car, head gasket. You know, same thing. Okay, there, and we'll come back to this later, but that's one way to handle a situation like this. Now that isn't a dead end, but it's a T, right? So they have a T in there. You see the valve, the red valve there by the fellow's foot. Okay, what's happening here when you pressurize this line is you got all this pressure coming down here, okay? And it's got a force pressure in an area. It creates a force, and that's going to take this line and, you know, try and do that with it, right? It's going to try and bend it back and work that valve out is what it's going to do. So the one solution there is just to take what's called a thrust block. It's just a concrete block that's poured on site. Now what the thrust block does is it connects to the valve, and it also connects to the back of the trench where that hasn't been dug up, and it should be strong dirt, and it spreads that force out and attaches the valve to the back of the trench, which should be the stronger dirt. Okay? That's the simplest solution. Now what's the problem with that 10 years from now? What do you got to do if you go? Yeah, exactly. And again, that's another one of them things where I prefer talking about that in the classroom than I do to actually be out there doing it. Okay. I wouldn't want to have to get that thrust block off of that valve if I need to replace that valve. That wouldn't be much fun. Okay. Yeah, that would be. So there's other ways of reinforcing connections and things, different connections you can use, but that is still a pretty standard way of doing it. Okay. We'll look at that later. Okay. All right, let's have a look at this one here. If we're good with all that. Now this comes up in a few places. If you build a dam, you're building a wall in a river. Okay, I got that sketch in there. It's 3D. It's 3D. Okay. A dam would look something like that. Okay. So you're putting a wall across the river with the intent of raising the water up for some purpose, making a reservoir or something. You're going to get pressure that builds up on that wall and tries to push the dam down the river. That's what it tries to do. Okay. So it's kind of, I've got yours kind of 3D like this. Now let's have a look at this. Now, a couple of things. First thing is, the wall is 10 feet high. The water is 8 feet high. What we're going to do is relate the pressure to the height of the water. Okay, as you build up the water behind that dam. So you're going to want the pressure at the top, which is 0, of course. Okay, at the top of the water surface, the pressure is 0. And then what's the pressure at the bottom? Which number would you use to find the pressure at the bottom? 8 or 10?
8.
Yeah, 8, okay? Remember that. The height of the dam doesn't matter. What matters is the height of the water, okay? So that could be, I think they call it a red herring or something like that. You know, just look at the water, not the dam, okay? Okay, 8 feet down, what's the pressure down there? Yeah, what is it, 3.464? So 3.46, okay, thanks. Okay, so what we're going to have here is the pressure at the top is 0, the pressure at the bottom is 3.464. So if you look at the pressure distribution, so to speak, it's a triangle. It's big at the bottom, it's smaller at the top. Okay, so what you're going to want is the average pressure. Okay, because the pressure varies depending on where you are. So the average pressure will be 3.46 plus 0 over 2, which is 1.73 pounds per inch squared. Okay? So pressure at the top, pressure at the bottom, find the average pressure. That's the average pressure pushing on the whole dam. Okay? Now there's a quicker way to get to that. And the quicker way to get to it is to get the pressure, what, at a 4-foot depth, which is the average depth. So rather than calculate, it's easier calculation if you just go 4 feet, which is the average depth, times 0.433 psi per foot. That's the easier way to do it, okay? And that's the 1.73 pounds per inch squared. Okay, so I would suggest just find the average depth and then find the, do it that way. Okay. All right. Now, 20-foot dam, 8 feet high. What's the area going to be there? Be careful. What area would we use for this?
Asking for inches.
Yeah, watch for inches. Okay, not feet, inches, because we got PSI, pounds per square inch. Okay, so you're going to want the area of the dam in square inches. Okay. So it's just watch the units kind of thing. 20 feet, 240 inches, I think. 8 feet, 96 inches. Is that right? Okay. So you gotta convert. So I just did it in my head, but you know, whatever. 12 inches per foot. That's so I got the 240 inches by taking 20 times 12, and then the 8 feet. 12 inches per foot, 96 inches, okay? So 240 inches long by 96 inches high. Okay. So you want the area. And it's going to be big. I mean, these large objects like dams and water tanks, they got large areas in square inches, of course. So we multiply that out and get the area. Uh, 2340, 23040. Okay. And then just multiply it out. Okay. That's the area. You got the pressure. Multiply them together, you'll get the force. And once again, you're going to get a big force, okay? So when you build these dams, you know, there's a lot of force trying to push them down the river. They have to be anchored into the walls of the river, into the banks, and also down at the bed of the river too. So they put extra walls on the dams to embed them. And that's also, that happens, you also get the water, the pressure builds up behind the dam and it pushes the water under and around the dam. It's called piping. And so, of course, you want to be sure your dam's functioning properly. So, you know, you build them like that. You put head wall extensions in them, wing walls, and you put toe walls in there too. The whole idea is to anchor the dam and also to prevent the water from being pushed around and under, because that'll cause a lot of problems if that happens. All right. Come on. There we go. So we're doing all right with that? We look at one other here. Okay, we good? Let's say we've got this here, and let's change it. Let's make it a circular, like a porthole or something. Round window, 24-inch diameter. I'm on page 81, but I'm changing it just a bit. I'm making, instead of square, I'm making it a round porthole kind of thing with a 24-inch diameter. All right. So I'd find the area of that, and then I'd find the average depth. And then I'd find the pressure, average pressure, and then the force. So that'd be the way I'd figure that out. And I don't know what this is going to be. I think it comes out roughly 2,000 pounds, but I'm not running it this way, so I don't know. But then stuff really adds up. I don't know if you ever go to the Oregon Coast Aquarium. They've got that glass tunnel, don't they? And you know, that thing is thick, right? I mean, we're not messing around with that. So sometimes the pressure isn't all that high, but the area is quite large. And when that's the case, you really have to account for that. I think I screwed up here, 11 feet. Yeah, I've got the wrong pressure. I hit a wrong button. $21.40, something like that. good. All right. Think we're good with that? Any questions? All right. Okay. You good? No one's going to start at that.
No, about 2153.
2153?
My
Oh,
fresh
sorry.
is different.
Is it? Okay.
Yeah, I got 4.76.
Okay, I think you're right. I think yeah, I did. I got a typo here. My bad. Thank you. It is 4.76. All right. Now I did that on purpose because you see if when I see how easy it is to fix that error when I show all the work, I can just cross it and just track it down. So I do that on purpose. Sometimes I make mistakes just to illustrate that point. Thanks. Maybe not. Maybe sometimes I just screw up. Who knows? Okay, 2154, 55, whatever. 21. Yeah. Okay, my bad. Okay. 2150. I got 55, but again, it's just rounding. Who cares? Okay. All right. So, you got any questions on that? Okay. I got a meeting to go to on Friday, so I'm not going to be here. Okay.
Oh,
Yeah, no.
I'll be here.
I'd rather be here than in a meeting, but that's life. That's what I got to do. Okay. So, but I do want to give you some stuff to do. So 8.1. 8.2, well, how about when I do this different? Chapter 8, 1 through 9. That's what I'd like you to do. And that'll be due Wednesday. We'll go over any questions, 1 through 9. And we'll go over any questions on Monday, okay? So, and this is basically 8.1, 8.2, 8.3. Now, I'll have answers posted in Moodle, okay? So, except for number 9. Number 9 is kind of a little bit of a challenging one. Which one? Hang on, whoa, hang on, hold it. I think that's the wrong chapter, isn't it? Yeah, that's the wrong chapter, I'm sorry. Hey, just scratch that, I'm already ahead of myself. Let me get this straight. Yeah, I've skipped ahead, so hang on. So that's what I have there is incorrect. It's chapter 7, 1 through 11. And the answers will be in Moodle, okay? Most of them are pretty quick. That's the problem.
You said due
Wednesday, so a week from today. So that'll be the 16th. All right, so are we good?